we saved the best for last. So, so directed energy deposition is kind of my forte, my background, and I got started in DED 10 or 11 years ago with a guy that's sitting over here that's going to speak next. So I thank you again for your mentorship. And so the cool thing about directed energy deposition is there's really no limit to how big something you can make. So the idea of building larger parts, you know, something that's bigger than a microwave oven or bigger than a cubic yard, you know, is doable. The idea of being able to add details to something that exists already, so doing critical part repairs. A lot of times we've actually started a build in powder bed fusion and then used it as a base or added features to it with directed energy deposition. So it's a very, very versatile technology. We're seeing over the years much more demand for DED. And 6 years ago, we added our DMG hybrid machine. And so that combines traditional manufacturing with directed energy deposition. So that's an incredibly powerful machine. If you haven't had a chance to look at it yet, when we go on our tour, we can do that, as well as I think Optomec, you're going to be talking a little bit more about your hybrid work as well. So without further ado, Lucas Brewer.
I'm Lucas Brewer, so I work for Optomec. I've worked at Optomec since 2003. Optomec is located in Albuquerque, New Mexico. We have a couple sites all over the U.S. and a couple internationally, but the main site's in Albuquerque. That's where I head up the lens applications engineering team. So the team in Albuquerque is really tasked with doing proof of concept work. So if you had a part and you wanted to know if you could add a feature to it, you would actually come to our group and we would potentially do that proof of concept work for you. So we're always getting new and exciting ideas in the applications group, and because it's additive, you know, there's a lot of education needed for everybody, and that's part of what our group does. I also manage the customer support group in Albuquerque, so I get to work with the customer in the beginning, and then I get to work with them in the end when they have their system. So I got to make sure we don't tell any lies or anything in the beginning, because I've got to support them then at the end. And then another thing is Optomec is commonly referred to our technology as LENS, laser engineered net shaping. It is the same as DED, directed energy deposition. It's just when the Sandia developed the technology, there really wasn't a DED category, so they had to make a category. Start up this video. I'm gonna leave that running while we talk about some of the things that DED does. So if you look at the part in the upper left-hand corner, there's a deposit that's happened on the inside of a bore. So that bore, you know, you could imagine something about that size. We've actually got a head that'll go in there and deposit inside of that. So, and then the part that Jeff is talking about, the powder bed part, is just to the right of that. So they had some powder bed parts that were just slightly too short, and they're able to go and add the material with DED. So you can see one of the strengths of DED is the fact that it can deposit on non-planar surfaces. So whereas in powder bed, you're kind of dealing with a flat surface, you have the wiper that comes through, it really needs the topology of that part to be very flat and symmetric. It doesn't matter with DED. We can actually go and, you know, print on a cylinder, print inside a cylinder. We've got several examples coming later. And kind of where our bread and butter is, the bottom left, you see some turbine blade tip repair, and that's one of the probably the most consistently exciting areas where DED is really shining. So if you fly in an airline in the United States, you have ridden in a plane that has DED repaired turbine tips in them. So It's been going on for decades. Millions of blade tip repairs have happened. And just so we're clear what we're talking about, this is a DED head here. And what distinguishes DED apart is you have, in this case, it's powder. So you have a powder feedstock that comes through nozzles. The laser comes through the center and hits the substrate, creates a molten pool of metal, and then we blow powder into that. There is DED wire, where you would actually feed wire into that molten pool of metal. This is DED powder, where we're blowing powder into that molten pool of metal. We can pass this around. The thing to note is the hole in the center is where the laser comes through, and the 4 tips are where So the other thing that allows us to do is in powder where we actually need it. So if you have a powder bed system, you actually have to be able to charge the full volume. With DED, you can do it in an extremely large part, but you're still only going to deposit material where you need it. So Optomec is a company, we actually, we do 2 technologies. The lens DED side, which is the metal 3D printing side. We have over 200 systems out in the field. It's more than that now. I know that's an old slide. And like it says, 10 million plus repairs have been done on turbine blade tips. So this is a true production in aerospace qualified repair. The other side of the company deals with printed electronics. And the way we do that is you create as long as you take a material that can be aerosolized, our technology will focus that through a nozzle and print very fine lines. So again, this is like a way to print circuitry with a non-contact metal method. So again, you can have a non-planar surface and print circuit boards onto it. One of the key applications there would be like printing the antenna on your cell phone. So on a cell phone, you have a GPMS, Wi-Fi, cellular, multiple antennas need to be printed on a cell phone. And instead of creating a circuit board just for that, the customer that we have actually prints on the case itself, which saves them space, which saves them lots of money. So we've been doing this for a long time, several decades or a couple decades. We actually purchased Huffman Laser 4 years ago. They were also the only ones who had been doing it for as long or longer than us. So that's a great team. We took them. They really looked at one aspect of the industry, which is aerospace repair, and they just went full bore into that. Whereas Optomec in Albuquerque really looked at multiple areas. We looked at repair, hard facing, 3D printing. So putting the 2 together, we really have some cohesiveness there. IGT repairs. So power, yeah, so if you're looking at like large blade repair, you have power, not just aerospace. And globally, we have 100 plus employees around the world. That brings us to the DED systems that we sell. So we have 8 current products in our product line. And if you look at the top left, the key there is that's an open atmosphere system built for aerospace repairs or IGT repair. It's an open atmosphere, and that's going to be a distinguishing characteristic between some of the systems that we sell. That was really Optomec and Albuquerque's claim to fame, is the fact that they did a closed atmosphere system, which enables them to do materials like titaniums, aluminums, reactive materials. To the right there, you have the MTS series of controlled atmosphere or open atmosphere systems. That's a hybrid. That's where you get the CNC milling machine paired with the additive print engine. So what you're looking at is there's a MTS 500, which is a 500 millimeter worth of travel, and then 860 millimeter worth of travel for the second system. Both of those can be open or closed atmosphere. And then you have our classic series of systems. Those are all, they can be open or closed atmosphere. Typically, they'll be closed atmosphere so you can do the reactive materials. And then in the bottom right, you see the what used to be called the 850R, which CCAT purchased 11 years ago. Now it's considered the CS 1500 millimeters worth of travel. The two areas where these systems really kind of shine right now. So if everybody keeps asking what's the trend, the trend for DED is really large part builds and repair. So I'm going to show some large part examples. I'll show some repair examples. It does build at a fairly fast rate. So that part on the left is Inconel 718. That was built in 8 hours. So 300 millimeters tall. The whole part was built in under 8 hours. The one to the right of that is a 16-hour build, 500 millimeters. And then the one on the far right, that's Tie 6.4. So not only is it large, but it needed to be built in an enclosed atmosphere. And that was built in 20 hours. One of the things that we were able to do with that one is it's a large truss rib for an aerospace company, but we're able to use the substrate itself as part of the build. So 1 inch worth of material was existing material from the substrate. We just printed on the top side and the bottom side, and that was finished machine. More repair examples here. So one of the more offbeat ones, that spiral gear that's there is from a local retail a food processing plant in New Mexico, and it was December timeframe. They walked in the door holding this gear, and apparently this gear spins the entire production floor in this one room that makes tortillas. So they were completely down right there around Christmas time, and we were able to repair it like under 12 hours and give it back to them. They got it finished machine and got their production floor up and running. The other one there, I think that's also in power generation. So the shaft itself is about 2 foot in diameter, stainless steel. And I believe the shaft was 20 feet long. So it's stuck out the side of the 1500. So it was done in open atmosphere, even though it's a closed atmosphere system, but it just kind of shows the flexibility. And then one of the enabling technologies for us for turbine blade repair is a software vision system called AutoClad. All of the blade repairs that we do, they have to be very precise. The alignment has to be very precise, or you're going to shoot the laser down the side of the part. So given the variation between each part, these are pieces that are in use. They're thin pieces of metal. They're under tremendous load, so they're not all the exact same shape when they were originally produced. So AutoClad will go in and find the profile of the part, readjust the existing tool path. That tool path isn't just location based, it's also got a recipe, which is the process itself. The process itself has laser ramp up, ramp down. It's really fine-tuned to make sure that you get enough buildup in the thin areas without overshooting. All of it is tied into the process recipe. And the nice thing for the user is the user really is just click and go. The system will take the blade under the camera. It'll go and find all the locations that it needs to find, automatically alter the tool path, and then take it underneath the deposition head to do the entire deposit. AutoClad is, it's really just one means of generating a tool path that we have at our disposal. One of the popular technologies is 3D scanning. There's different methods. You could use touch probes, 3D scanning. Whatever method you use to actually find the location of the blade, we can take that information inside of Mastercam, which is what we use to generate our tool paths. And, you know, using the plug-in criteria that we have to develop the process, we can trace a 5-axis path, simulate it, and generate it. This is an impeller for, I believe this is I believe it's for power generation on a vehicle. But anyway, you can see that's a fairly complex tool path, but all we really need to do is find the center line. So we could use AutoClad, we could use a touch probe, we could use 3D scanners. This particular part to do by hand takes 15 hours, and we can do this part in under 30 minutes. Just some of the more aerospace repair examples we have. We have the knife edge seals, which is that top left corner where you're adding material to the two ledges on the bottom of the blade. The compressor blade tip repair, where you're adding the material that gets worn away on the tip. You also have the Z-notch repair down there in the middle, bottom middle. I think that's 12 different repairs or 12 different deposits for that one repair, and all of that can be located with AutoClad automatically, printed by hitting go. One of the ones that's getting more and more interesting in the industry are blisk repairs. So with all of these other aerospace repairs where you have blade tips, you can take the tip by itself. You can have an array of tips sitting on a tooling plate, but with a blisk, everything is one big piece. So you end up needing a very large system that can handle, you know, the array of blisks that come through. We've done several blisk repairs at Optomec. Our 850R is actually, or the 1500 was designed to do blisk repair. So to handle all these different repairs or 3D builds, we need a really flexible system. And so DED powder is really flexible as for one. If you think about the amount of control that we have over the powder feed rate, that allows us to do very fine prints or to do very heavy, bulky prints or high deposition prints. But to enable us to do that, we also need to be able to adjust the laser spot size. And previously, people would do this by either defocusing the laser, which gives you some questionable beam quality, or they would use a fiber swap. So you'd have a laser with a coupler, you'd use a 200 or a 400 or 600 micron fiber, and that would adjust your focus spot size. The problem with that is these machines are very dirty. They're, you know, you've got to have somebody go in there and actually do the swap. So the chance that you damage a fiber is pretty high. So what our engineers came up with are these shaping optics, and it's a turret of shaping optics. So the first position would be our standard setup where there's no shaping optic. It's that gives us about a 650 micron beam with no shaping optic. Then we can bump that up in discrete sizes. So we can go to 1.3 millimeter with the next shaping optic. We could do 2 millimeter with the next shaping optic, 3, 4, and so on. The nice thing there is that this is not just giving you a bigger beam, but it's giving you a flatter power distribution. So that flatter power distribution is really kind of key when you're doing high power deposits. Without it, you end up with a hot spot, say in the center. Sometimes it's typically off center, and you can vaporize material in that one spot while the rest of your melt pool looks beautiful. Nice flat profile allows you to have nice gentle deposits. Because that's controlled with a stepper motor, it's actually can be CNC programmed. So within a tool path, I can call, different configurations of spot sizes. So over the years, we've had to develop so many different head configurations, and it's the ability to be able to deposit on some odd shaped parts means you're getting into some odd areas that don't have great accessibility. So we do have standard nozzles, we have limited access nozzles, we have deep repair head nozzles. All of these on our new equipment are 3.1 head. You're able to do a quick change because we have the systems many of them are under atmosphere. We have to be able to do everything through these gloves. It's really kind of awkward. So this is a tool-free changeover. Some of the other heads that we have a nice fine feature repair head. We have a high output coaxial head, a high standoff head, and it's I actually have a video that I'll run where you'll kind of understand why it's nice to be able to step away from the part, because that kind of pulls you away from obstacles that are on the side. And then the deep repair head. This deep repair head is cool because you can actually you can stack tubes together, and you can go into a tank barrel, reclad the inner diameter of the barrel. This is a crankshaft that a customer brought to us, and you'll see the numbers kind of marked off on the different areas. Notice the only one that's in red is the one that's extremely hard to get to. That's the one that's in the center. So you have to have a special head for that, because nobody's got a head that fits in between those two lobes on the crankshaft sitting on their shelf except for us. And I couldn't have designed a better head to do this actual repair. So what we're showing is we've imported the model inside of Mastercam. The nice thing about Mastercam is it supports so many different file types. Anything you can think of, it's got support for it, which is really nice for the apps group because we're constantly getting different file types. This is going to show that the apps engineer actually had to create a false surface so that the head could, instead of coming straight across, if you could imagine going straight across and coming into the corner, we'd actually collide, even if you have a small head, because the center line of your deposition head would still force the rest of your head to collide. So what he did is he created a false surface that'll allow the head to sweep like this, or in this case, the part to pitch. Inside of Mastercam, we've got several different macros that you can call them. They're multi-axis, open contour, a lot of different approaches to come up with a process for your given repair. Inside of Mastercam, it's got all our recipe information. So there are libraries of material which also hold process information. So I could create a toolpath for this, tell it it's Inconel one day, tell it it's Tie 6.4 the next day, and it would actually change the process parameters for me just based on me telling it what material we're using. We'll get to the part where it's just depositing. Money shot. This is standard NC code, so most machine tool operators can look at this and know what's going on, which is one nice thing about training people. If they have machine tool experience, that's one less thing for them to have to worry about. So you can see that the crankshaft is kind of positioned at an angle. That's because it's depositing here up in the corner furthest away from the table. The area for repair, the bearing journal, is actually off-centered, so that's why you see the head having to go up and down. It's actually doing X, Y, Z, and rotate moves during the deposit. There, we're at the center of the part, so we're able to do the center portion kind of at a flat attack angle. One of the things that you'll notice is the laser keeps going on and off in certain spots. It's because there's a oil hole. And we don't want to clog that, so it's just shutting off whenever it gets to that oil hole. And then it'll run through and you'll see that it actually pitches over again to help you get into the other side corner. The temper, so it's basically, you know, if the material needs to be heat treated to get to rot material properties, I mean, so if it's heat treated for rot material, then it needs to be heat treated again. So, and really it's very process dependent for us. So I could have something that's a nice hot build and it'll be almost annealed. I could have something that cools very rapidly and it'd be very much stronger than your normal material. And this particular one we did in the hybrid system, so we're able to go back and refinish that. You wouldn't refinish this part with a hybrid machine, but it's a cool demo. And then everybody's talking about process monitoring or process control. So Optomec does offer two options for process monitoring and process control. The first one is the melt pool sensor. Optomec's used this for a long time. All the melt pool sensor does is it looks at the area of the melt pool and it tries to maintain that by varying the laser power. So basically, if the part gets hot, it needs less laser power to maintain the same size area melt pool. So we can drop laser power as we're building up and we're pulling away from the substrate. The other one is a thermal imager. What this thermal imager does, it actually looks at the true temperature of the melt pool. So that's very key because one, you can plot it over time and see that, you know, you're maintaining the same temperature, which basically is maintaining the same cooling rate, which goes to your material properties that we were just talking about. The key with this thermal imager is it's a 2-color pyrometer. So if you have a single color pyrometer, you basically have to calibrate every material that you're going to run on that system. You'd have to plot a temperature curve. With the 2-color pyrometer, you're looking at the difference between the low pass and the high pass. And that means regardless of the emissivity of the material, I still get a temperature reading based off of the low and high pass differential. So the melt pool sensor itself, the key there is both of them are trying to do the same thing. They're both trying to affect the cooling rate of the part, and you want to maintain it throughout the entire build. Whether you've increased the amount of area that you're printing on a certain layer from another layer, or if you know you're pulling away from a mass of material that helps act as a heat sink. Either way, we're trying to control the cooling rate, and adjusting the laser power by looking at the area of the melt pool is a means of doing that. There's a much more direct way, which is the temperature method, which is what the thermal imager does, the 2-color pyrometer. So the interesting thing is when you're using a melt pool sensor and you're using it on the center of the part, you get a nice full reflected image of the melt pool back. When you're on the edge and part of the laser is actually falling off the side, the area method doesn't work as well because you're not getting, you'll never get a full melt pool area back on a contour. Whereas the temperature of the material should still be the same for the contour and the inner fill portion. The thermal imager will allow you to do that. Both the melt pool sensor and the thermal imager, we've tied laser power, powder feed rate, position, so that the data log of your temperature mapping actually can generate a 3D model that tracks the temperature of the part. In the thermal imager closed loop version, it's actually varying the laser power and dwell times to help affect the temperature. So in between layers, it'll pause to allow you to cool more rapidly, or it will not pause and allow you to maintain the built up temperature. And then it'll also control laser power. I think that's it. Does anybody have, yeah, this is just talking more about the parameters that it data logs. Questions? So we work with a third-party CNC manufacturer. Yeah, they've got the expertise in it, so we just use it. And so the questions regarding hybrid, and in this person's case, they're actually looking at wire and hybrid, which is both are DED. And the question is there a difference in material quality from wire to powder? I believe that's what he was getting at. With and the answer truly is not really. You do have a little bit more control with powder because I can do much finer with the same feedstock. I can do very fine feature to heavy deposition. With wire, you're kind of stuck with a core size that you're running. So whatever wire diameter you have is going to kind of define what deposition rate you have. So if you try to do fine feature with a larger core, it's you know, that's not the best solution. You'll get hotter, you'll get a hotter you know, deposition rate than you may want. So then you have to look at distortion, material properties, but basically both can be controlled. You just maybe have to plan a little bit more with the wire. Other ones? So you do it over here. You have subject material in the pods on top of it. What's that interface? Yeah, usually so we'll refer to the heat affected zone. The heat affected zone will penetrate into the substrate. So it looks usually like 5 layers. So if you're doing 10 thousandths of a layer, you'll get 10,000 or 50 thousandths worth of penetration. But oftentimes the deposit itself, I mean, it's a solid, it's all one material at that point. So if you have a break or you do a tensile test, it can break in the substrate, it could break in the deposited material, it could break at the junction if you had an issue, but if you don't have porosity or lack of fusion, there's not an issue there. So some processes happen to skip apart. We don't typically do it, but there are some aluminums that we're looking at. So some of the issues that we have with aluminum is they have some porosity on the edges, and we're able to use hipping to get rid of the porosity on the edges. But for the most part, it's not needed for a lot of materials. So we've printed moon dust. People have printed ceramics. I mean, basically, if it'll melt, you know, you can do something with it. But usually, like the rule of thumb is if you can weld it, then you can probably use DED to print it. We've had some stuff with like cubic zirconium, you know. I don't know, like just not a material I can't do. I don't know. There's varying degrees of success, right? So if you come to me with moon dust and I give you a lump of moon dust afterwards, that's pretty cool. You know, don't go building airframes out of moon dust. Say that again? Yeah, glass, so it's very brittle. So it's gonna crack before we get anywhere with it. If we're allowed to, it's nice to dull up the surface, but we're not allowed to in many cases. So we can process a nice shiny surface, finished surface. It's just part of the process. So we know that we need to use more laser power in the beginning because it's going to be reflected off. But if you allow me to, I would prefer to dull up the surface. And then of course it just needs to be clean, free of, you know, contaminants. Yeah, so there's both approaches, right? So if you want to do the repair with the same parent material, that's great. If you want to have a harder material to extend the life of the component that you're actually running, that's an option. So it's called gradient material. So we're able to go from material A to B. We have up to 4 powder feeders on a system, so we can do alloying on the fly. With that, you know, just they have to be compatible material, but there are cases where you could go from material that's not like A is not compatible with B, but you put C and D in there before you get to B, and you can work it out that way. Very flexible, so it's great for wear coatings and corrosion. You can actually make the repair maybe better than the original part.